Thank you, and thanks also very much to the reviewers and to the awards committee for bestowing this great honor upon us. We are very pleased, and it's really a great pleasure to get this award in this wonderful team of co-authors. Now, since the time is very short, I want to jump right in. Ontology-based query answering is probably familiar to many in this session. The general idea is that we have a database and a logical theory, and we are interested in the query results which are entailed by this input. Now, when I say database, often I think of this as a graph or hypergraph, but this is just a matter of perspective. Now, in recent years, many different formalisms have been studied in this context of ontology-based data access. You see some here, but in this talk, I will mostly focus on Datalog and the extensions of Datalog that you can see highlighted here. So Datalog, even if you don't know it, very simple rule language of Horn rules with universally quantified variables. Disjunctive Datalog adds disjunction on top of this so that we can have non-deterministic choice, and existential rules add existential quantifiers, allowing us to express things like this ontological statement here, which you would often find in ontologies. Right. Now, as you can see from the complexity column here, things get very complicated very soon, in particular for existential rules. This is no longer decidable. RE is for recursively enumerable. So people have studied many different ways of finding decidable fragments. And one way of doing this is the so-called chase algorithm. Now, again, you don't need to know the details of this procedure. In principle, it is a very simple process where we simply apply rules bottom up in a forward chaining way until saturation, which of course with existential quantifiers may never happen because an existential rule can require us to introduce a new element, and therefore our database can grow and grow, and this might never stop. Now, if it stops, we can use this for query answering and therefore obtain a decision procedure. Various kinds of chases have been discussed in the literature. I mentioned three here. The details are not so essential. Skolem chase is the simplest one. Standard chase is a bit more refined. It will terminate more often. And the most general one is the core chase. Skolem and standard are widely implemented. Core chase, not so much. So this gives us a number of further questions in the OBDA setting, because each of these chases gives us a fragment of rules for which it will work as a decision procedure, because it will terminate, and we can ask which complexities it has. And as you can see here, this is not known in many of the cases, but this talk will give some answer to the question marks here. Now, if you see even for a simple case like Datalog that it is polynomial in complexity, you may ask whether conversely it can actually express all the polynomial queries. So is it true that Datalog can express every query that can be decided in polynomial time? What does it actually mean to do this? So a query in this general sense, which can be expressed in polynomial time, would correspond to some polynomial time algorithm that takes a database as an input and produces yes or no as an output. I'm talking about Boolean queries here. Of course, this is not really true in this picture. The reality is that we somehow need to serialize the graph and then work on some tape representation, some string that can be given as an input to an algorithm. So this is something we often don't talk about in computer science, but of course it is necessary because algorithms are defined on this level. And actually, we can even represent such a tape as a graph structure, and we could again use Datalog to process it. And it is well known that Datalog can simulate Turing machines up to polynomial runtimes based on such inputs. So this looks very promising, and we can really ask, can we express all the queries? Now, interestingly, after this introduction, maybe the answer is a resounding no. We cannot express all queries, and the reason for this is quite simply already that Datalog does not have negation. So without negation, we cannot have a query which asks for the absence of some information in the database, which of course can be very easy to check with a polynomial time algorithm, but which cannot be expressed in Datalog. And mathematically, this property of not having negation, of being monotonic in this sense, is also expressed by saying that Datalog queries are closed under homomorphism. And so you have one piece of the title that we have in this work. Yeah. So closure under homomorphism means that if you have a database and it has a homomorphism into another database, which always means the other database is somehow more informative than the first one, it has more information, in this case a queue, then every Datalog query that matches in the first one also has to match in the second one. And homomorphisms can even go further. They can even collapse elements, and still this database contains more information than the one before. Yeah. Okay. But even if we consider only homomorphism-closed queries, Datalog cannot express all queries that are polynomial time, but that's another story for another talk and not for these 12 minutes. So this is the status. We know the expressive power of Datalog is somehow a subset of hom-closed p-time. The same is true for the Golem chase terminating existential rules. But as soon as we go to the standard chase or to the core chase, or as soon as we add disjunction on top of this, not much is known. Yeah? And so this is the main result of this work here, namely that existential rules for which the standard chase terminates on every input and with every fair rule application order can express all decidable hom-closed queries. So that's a very strong result and a very general one, which in some sense gives us the maximal conceivable expressivity for such a fragment, which is monotonic and decidable. And because this is maximal, we immediately get that the other more general fragments also have the same expressivity. They can't add to this because they are still decidable as well, and they are also monotonic. So let me give you a glimpse on how we prove this. There are 3 steps. The first step will be to get somehow from the database to the tape so that we can run a Turing machine, because this essentially is the reason why Datalog, this is the thing that Datalog already cannot do, to serialize the database into a Turing machine tape. And it starts with the big problem of order, because a database like this is not ordered in any way, and we need to have an order in order to write a Turing machine tape. And the best thing we can do to obtain this with disjunctive Datalog is actually to guess it. So we have rules like this one here saying that if x and y are elements, then either x is equal to y or x is not equal to y. And if it's not equal to y, then one of them has to be shorter, smaller. Yeah? So if we have such rules, of course, they are quite blind in what they produce, and we can get many possible models. So one model would be something like this, which looks fairly reasonable, where we have A, B, C, D as an ordered set with transitive bridges. Of course, the order could be different. We don't have a preference of A, B, C, D. It could be D, A, C, B. But there could also be other cases where, for example, 2 of these are considered equal, or even 2 pairs are equal, or maybe all of them are equal. And we cannot even prevent cases where there are some cycles in the order because we are just guessing this wildly. Yeah. So all of this has to be accepted, but it is not a problem for us because Datalog, disjunctive Datalog entailment is cautious entailment, meaning that things are only true or are only entailed if they are entailed in each model. And so it doesn't cause us problems here to have such wrong models, because all of the wrong models are, in a sense, stronger. They are more informative in the sense that they represent databases that are more informative. So if the query is true on any of the good ones, it will also be true on the bad ones, and this will not change the result. Yeah. Okay. But this is not enough to get what we need when we talk about order in Datalog, because this is not a suitable successor relation. Not even this nice one is, because the relation here is transitive. Datalog cannot say what the successor of A is, for example. It could be B, C, or D. All of them are in a successor relation in a sense. The only reason why we would prefer B is that there is no element between A and B. But of course, checking this requires negation, so we cannot do it in Datalog. To solve this problem, we unravel this order and create some kind of tree structure. This can be done by existential rules, and it will give us something like this with different paths that you might take through this graph going in the forward direction. And the nodes I have here, they also have colors and the letters, but they are not the same nodes as above. They are representatives that we create with existentials and that merely are associated with the original nodes that they represent. And you can see here that the paths we get are not all the paths that we wanted to. I mean, the right one is good, but the other ones are somehow too short. And indeed, they will represent only a sub-database, so with less information. But this, again, is no problem here, because we will, in the end, simply run the Turing machine on all of these paths. So if some of them has less information, because we are talking about hom-closed queries, they will be less likely to accept. But as long as there's one which has all the information which will accept, we are fine. Okay. So getting from such a tree to a tape is then a technical exercise, which is a bit tedious. We have all the details in the paper, but not too hard to do. First of all, we can copy some of the basic relations that we have from the model into the representative tree. And then we can enumerate the nodes in this tree by assigning to them decimal or binary representations of numbers, which we again create existentially. So these little gray zeros and ones are new elements that we introduce, and we count up starting from the root to produce these numbers. And so having all of this together, it is then possible to actually create a real Turing machine tape with a real full binary serialization of this whole thing, which will look somewhat like this. There's a bit more needed. We need to know about the absence of some facts, which I have not talked about here, but the ideas, the main ideas I think you got from this. Okay, so this solves the first problem, because once we have the tape, simulating the Turing machine is fairly easy. What remains to do now as a second step is to ensure termination, because the thing that I have done so far is not going to ensure termination. We have disjunctive existential rules which can create infinite models because of situations like this one here. If we guess a cyclic order and we try to unravel it, it will become an infinite tree. But thankfully, these cases are easy to detect in Datalog. We can detect cycles, for example, in Datalog. And so we can apply a termination technique that we call the emergency break. This is a construction we have introduced in an earlier paper, but now generalized to make it applicable to more settings. And it works like this. So first of all, we, very sketchy here, yes, prepare an inactive structure. I call this inactive, and it's gray in the picture. This is what it means so far. It doesn't have a color. For which any further model expansion is redundant. So this node is its own child and parent. You cannot add any further children to it by applying rules. It's done. It's maximal in a sense, containing into information-wise. Then, after you have prepared this structure, you make sure that all the nodes in your model are connected. So they all have this as a child. But this doesn't affect any of the reasoning because the element is inactive. Then the rules will basically ignore it. But we always prepare this connection. When we introduce a new element, we make sure it's immediately connected. And then whenever we detect a problem like this cycle, we make the structure active. And now we have the color here, meaning that now all the elements, intuitively speaking, can see this, and they all have this as a child. And so in this very moment, when we apply the rule, when we make it active, they will have all the children that they could ever wish for, and the expansion of the tree will stop. No matter how far it got to this point, in one step, all the expansion all across the model will stop and the chase will terminate. So this is the emergency break in a nutshell. Okay, and finally, we need to get rid of the disjunctions. And for this, I just have this one slide. The very rough high-level idea there is that we take the disjunctive reasoning that you could visualize like this, where you have possible worlds that are extended, and you represent this reasoning in existential rules by turning every possible world which represents one disjunctive situation that you could consider as one element in your existential rule reasoning. So we basically reify, we introduce representatives for the worlds, and we have everything in one model that we formerly had in many models in disjunctive Datalog. That's the high-level idea. The challenge is to make this actually terminate, because if you naively do this, it will just allow you to create more and more worlds as you go along, even for rules that you have applied before, and it will never stop. And to make this stop, we use a special technique which we have introduced for set modeling some while ago. Okay, so this is it. And my time is over. Here are the results for you to read through again, and a bonus theorem that I didn't have time to mention. And I'm happy to take questions. Thank you.